But what we do get is obviously we get an increase in the amount of blood that the heart's pumping out. So it pumps faster, it pumps harder, it pumps more efficiently, and we get an increase in heart rate and an increase in cardiac output. Now, when I move on in a second to the adaptations that actually occur because of all these stimuli, the adaptations in the heart are relatively poorly researched. And one of the things we've got is we do know that this doesn't seem to have much of an effect on adaptations, but there may be an effect of this increase in heart rate. Just by raising your heart rate, there may be some sort of stimulus to the heart. But as we'll see, that doesn't seem to necessarily be the case. So that's generally what seems to happen when we're doing resistance training. The actual physiological responses that occur at the muscular level and partly at the gross cardiovascular level are really not that much different than what happens when we do traditional cardio. So the question is, that may happen, during exercise, but that doesn't necessarily imply that the adaptations will be the same, because there are a host of other things that go on when you're doing resistance training compared to cardiovascular training or cardio training. For example, you've got increased tension on the muscles because of the resistance you're using. But we at least know that some of the responses are pretty similar, and the responses that are similar are the ones that at the moment and what are predominantly evidenced to induce those cardiovascular adaptations. So this is the last slide that I'm going to go through. Just going to go through the adaptations that actually occur that are shown to actually improve your cardiovascular fitness. So we've taken the graph, and let's assume that we're going to perform a training program, getting people to perform high intensity resistance training, i.e. training to failure each time they perform an exercise. What we're going to assume is happening is all those responses that we just spoke through, they're going to be occurring whilst they're doing the resistance training. When they get to failure, they're going to have an increase in maximal anaerobic, aerobic metabolism, increase in AMP to ATP, AMPK is going to be activated, all these different things that are going to be stimulating cardiovascular fitness improvements. So again, what we did is we took each of the components that are thought to improve measurements of cardiovascular fitness and had a look at what was actually happening in terms of the physiology, because we had seen that all of these measurements of cardiovascular fitness were improved, but a lot of different things actually constitute to those improvements. So if we take one measurement of, say, for example, VO2 max, there's a whole host of different things going on whilst we measure that are contributing to that end result. So what we wanted to do was work back a little bit and actually see what is happening in the body, what physiological adaptations are happening that are improving cardiovascular fitness. So again, we looked at the, wrong one. Is that going to go back? Yeah, there we go. So we looked at the metabolic, the molecular, and the cardiovascular adaptations. Now, again, what we did was we took the studies that had controlled intensity and the studies that hadn't controlled intensity and compared the results of the two. And consistently, what we found was the studies that had controlled intensity had their participants train to failure as opposed to just training to some arbitrary number of reps, 3 sets of 10. Doesn't matter what weight you're using, doesn't matter if you could have done 10 more reps, 5 more reps, whatever. We were looking at the studies that actually had their participants perform as many repetitions as they could. They trained to their maximum. And what we found, interestingly, was in terms of the metabolic responses, there was an increase in every study in terms of the mitochondrial enzymes. So the mitochondria, as I said earlier, that's the part of the cell that performs aerobic metabolism. And there are various enzymes in that part of the cell which perform all the biochemical processes that produce ATP in the presence of oxygen. And what all these studies tended to find was that these enzymes started to significantly increase in the amount that were there. So assuming they're not what we call rate-limiting enzymes, i.e. they don't have a maximal cycling rate, the more we get, the more efficiently we're going to be able to actually perform aerobic metabolism. And consistently, every time a study had the participants perform to momentary muscular failure, intense resistance training, there was an increase in mitochondrial enzymes, which is traditionally believed to be associated with endurance activity and cardiovascular fitness. In terms of the molecular things that went on, we also found that studies, again, that had performed resistance training to momentary muscular failure had an increase potentially in the number of mitochondria they had. Now, these studies had a bit of a problem in terms of methodologies again, because you can have what's called measures of volume or measures of density when you're looking at cellular things. And a lot of studies mistook density for volume. And let's say, for example, you take an absolute volume and you measure the amount of stuff that's in it. Well, if you look at it relative to the absolute volume, then you can say there's a density of da-da-da-da-da. If you then go to measure the density again and the absolute volume's increased, but the amount of stuff inside it has stayed the same, it will give you the impression that the amount of stuff might have been reduced because the density, the relative measure of that stuff compared to the volume has decreased. But what's actually happened is when you look at the resistance training studies, at worst, they have no effect on the number of mitochondria. Some people suggest that resistance training reduces the number of mitochondria because they falsely interpreted this density and volume measurements. But other studies actually show that mitochondria, the number of mitochondria you have, increase. So you get what's called mitochondrial proliferation, which is something that this AMPK molecular pathway controls. So, and this is a big topic as well, because there's a lot of stuff at the moment in terms of how important your mitochondria are to your health, not only your fitness. So the idea that you can increase the amount of mitochondria you have, produce new mitochondria, will mean that you'll be working more efficiently and potentially, you're improving your health through that as well. You also get a change in fiber types. So does everyone know that there are different types of muscle fibers? So on a simple scale, you've got your type 1 fibers and you've got your type 2 fibers. You can go into more depth with that and say there are different types of type 2 fibers, and you also have intermediary fibers which sit between the two, but you can go on and on and on. But essentially what you've got are your type 1 fibers are what you call your slow twitch fibers, and your type 2 fibers are what you call your fast twitch fibers. And your slow twitch fibers, your type 1 fibers, are generally more fatigue resistant. So they'll be able to go for longer as compared to your type 2 fibers. Now your type 2 fibers, again, with a kind of simplified change between them, you've got what are called type 2X and type 2A fibers. And your type 2A fibers kind of sit between the two. So they're powerful, like the type 2X fibers, but they're also more fatigue resistant. So they're like fatigue resistant type 2 fibers. Now what happens, again, with resistance training to failure is as you train to failure, over the course of a training program, your type 2X fibers start to change to type 2A fibers. So the fatigue resistance of your type 2 fibers increases, and that's predominantly because there's an increase in the number of mitochondria in them. So these type 2X fibers, which typically are more fatiguing, they increase their AMP to ATP ratio more drastically than the other fibers do. And this is what stimulates an increase in mitochondria in them. And eventually it gets to the point where they've become so fatigued over a series of training sessions that stimulus has induced an increase in the mitochondria in those muscle fibers. So they end up looking like type 2 fibers. So you end up with a more fatigue-resistant muscle as a whole, as well as an increase in strength. Okay, you also get an increase in type 1 fibers as well, which has been shown in a couple of studies. Now, the last thing to look at, again, is this gross cardiovascular improvements, because most people, when they think of cardiovascular, they think of the heart and they think of your arteries and your veins and your capillaries. Now, as we've shown, there doesn't seem to be that much of a stimulus to the heart, and the training studies actually tend to support that.